For this problem, we're looking at a frame which is made up of members BD, which is a rigid bar, and DH. There's also a wire which is connecting point C on the rigid bar back up to joint K. We have a line load acting over the right half of the rigid bar BD, and what we also know is that the temperature of the wire KC is being cooled by an amount of delta T where everything else is being kept at a constant temperature. We're going to start out by doing our usual first step, and that is to get as many equations as we can that are going to be useful to us from equilibrium. What I'm going to do is draw a free body diagram of member BD. I have the reaction force By and Bx, those two components for the reaction there at B. On the right hand side at point D we have the member force F2. We have the single force equivalent of the line load, which is W times L over 2. And then we have a member force F1, which is acting at an angle of phi, which from the figure given here, phi is equal to 60 degrees. My choice is going to be put x to the right and y up. And what I'm going to do is write down a single moment equation about B. The moment equation about B gives me an F1 sine phi. That has a moment arm of L over 2, and that will be in the plus K. The member force of WL over 2, that has a moment arm of 3 force L, and that's going to be in the negative K, as well as F2, which has a moment arm of L, and that's also going to be in the negative K. So from this, I make the observation that I have one equation, yet I have two unknowns. This, therefore, is indeterminate. Indeterminate means for us that we need to come up with some additional equations that account for the deformations of these supports, the deformations in this case for members 1 and 2. You might ask, why didn't I write down the summation of forces in y? Well, I could get an additional equation, but keep in mind that I would end up with an additional unknown there of by, nothing gained. I could also write down a summation of forces in x, but again, I would come up with one more equation with an additional unknown of bx. So basically, my simplest form here is just to use the moment equation. My elongation equations. So keep in mind that the member 1, the cable, is going to have extension due to the mechanical loads there of F1. So we get F1 L1 divided by E1 A1 plus alpha delta T. For member 2, F2 L2 divided by E2 A2. But it says here that there is no change in temperature. So that's what we've got. This is equilibrium equation 1, elongation equations 2 and 3. What we need to do is to be able to relate the elongations through some compatibility equation. So our compatibility equation is going to come down to, can we represent what's happening as this rigid bar will rotate about B? We don't know which way it's going to rotate, but let me assume that, for the sake of drawing a picture here, that as a result of the contraction of member 1 due to the temperature change and the applied loads along the right end, it's going to rotate this way. So we will say the rotation is like this. What this means is that I have a deflection on the end here, which is going to represent the elongation there of 2. If I come back and look at C, this is going to be the vertical deflection of point C. Note that VC and the elongation or the contraction there on 1 is not the same thing, because the contraction of 1 is along that angle of phi. We're representing here the vertical component of the displacement there for C. So for compatibility, we will say that from similar triangles, that VC divided by L over 2 is equal to E2 divided by L. This is L over 2. This is L over 2. So I'm looking at similar triangles here of this one for the left-hand side, and then I have the similar triangle here for E2 and L. So this is similar triangles. Similar triangle means I'm enforcing the fact that that bar is going to rotate in a rigid way. So this is our fourth equation. At this point, though, we still have, what, 1, 2, 3, 4 equations, and our number of unknowns are going to be represented by F1, F2, E1, E2, and VC. So we're still short in equation. But note that if we look at the wire, what we can say is that the elongation of the wire, that's what we need to bring in, is going to be related back to the horizontal component of displacement of C times cosine of the angle for member 1 plus the vertical component for the displacement of C times sine of theta 1. Let me go back to the picture. If we look there at member KC, we know that theta 1 is going to be measured from the x-axis back at the base in the counterclockwise sense. So theta 1 in this case is going to be equal to, if this angle is 60, it's going to be 360 minus 60, so that's going to be 300. We know, therefore, the angle theta 1. We also know that UC is equal to a 0. For small rotations of that bar, C is moving straight up. There is no horizontal component of the deflection there for C. So what I can do is combine these two together and drop out UC here. So that gives me 5 equations. And so at the solve stage, I have 5 equations and the number of unknowns. Let's make a list of those. I've got F1, load carried by member 1, load carried by member 2, E1, E2, and therefore our last unknown there is VC. So we have 5 equations and 5 unknowns. We have now got enough information. What you need to do at this point is simply use algebra to solve for those 5 unknowns from those 5 equations. Not as bad as it might seem. The equations really aren't that involved. So combine those in order to find the answer. So in review, what we have is a frame which is indeterminate. We're looking primarily at the rigid bar BD, and we're considering the wire and the rod 2, those are the two member forces we have, F1 and F2. We couldn't get those from equilibrium, so we had to look at the elongation equations for each one. There was the fairly common idea here that for the rigid bar rotation, we're going to use similar triangles to relate the vertical displacements of C and D. But there's this additional catch here that this VC here, we want that to be related back to the elongation of 1. It's not one in the same because VC represents two things. It represents a change in length of 1 as well as a rotation. And that rotation of 1 doesn't add on any elongation. So we get that from our truss equation here, and basically says that E1 is equal to VC sine of theta 1. That gives us all the equations we need to solve for our unknowns.